Hello students, in this video we will learn how to deal with standard two-port networks and how to get their Z parameters, Y parameters in shortcut way. Let's see. Let us start with standard two-port networks now. First standard two-port network is T network. Let's say this is Z1, Z2 and Z3. And let's say we have to get Z parameters for the same. How do we get Z parameters? Let's see. Assuming plus minus V1 here, plus minus V2 here, assuming current I1 here and I2 here. Let's say this is I1, this is I2. So by KVL to loop number 1, what we are supposed to get in loop number 1, you have to apply KVL. See, we'll get equation as V1 equal to Z1 times I1 plus, through Z2, two currents are flowing, which is I1 and I2. So I can say Z2 into I1 plus I2. Or upon expanding, you will get Z1 plus Z2 times I1 plus Z2 times I2. So I'll say this is equation number 1. Similarly, when you apply KVL to port number 2 or output side, what you are going to get is this. V2 equal to, you can see via Z3 only I2 is flowing, but via Z2 I1 plus I2 is the current which is flowing. So I can say V2 equal to Z3 times I2 plus via Z2, as you can see two currents are flowing, I1 plus I2. Upon separating these two, what we get? Let's say this is equation number 2. And now if you actually see a complete Z parameter now, by comparing with the standard format of Z parameter, you can see Z1 plus Z2 is nothing but your Z11. This is nothing but your Z12. Check it out. This is your Z21 and last this is your Z22. Let's substitute them in final Z matrix. What you are going to get? Z1 plus Z2. Here what you get is Z2. Here what you have is Z2. And what you have here is Z2 plus Z3. Now, the reason why we have solved this, just because at the end what Z parameters you get over here, only that you have to remember. Check it out. You have to remember this. You will have to memorize this. What is that? That is nothing but if you have Z parameter to calculate for T network that consists of Z1, Z2 and Z3, then Z parameters will be like this row wise: Z1 plus Z2, 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 Z2 plus Z3. So I request you not to actually solve for T network ever. Once you come across Z parameter, you can write it directly: Z1 plus Z2, Z2, Z2 plus Z3. So this is a shortcut to be remembered for any T circuit, right? Let's go to the another standard circuit called as pi network. Let's start with second standard two-port network, which is pi network. So as the name implied, it actually looks like pi. You can see in the diagram. But here elements are like this: YA, YB and YC. You should understand Y means admittance, and admittance have unit as mohms. That is mho, MHO, which is inverse of ohms. This is plus minus V1, I1. Again, this is plus minus V2 and this is I2. For this, we are supposed to calculate Y parameters. For calculating Y parameters, we go for KCL. Like for Z parameters, we go for KVL. So assuming this node as V1, assuming this node as V2, as you can see I1 is incoming, but then let's assume these two currents as outgoing. Let's apply KCL at V1 node now. At V1 node I1 is incoming, so we'll go for minus I1 plus second current I'm talking about, this current, where it is V1 minus 0 divided by impedance, but this time it is not impedance, it is admittance. So instead of dividing, we multiply by admittance. So next current is V1 times YA plus, as you can see this current, it is going from V1 to V2, so I can say it is V1 minus V2 into total admittance in the path, which is YB, equal to 0. So minus I1 can be taken as plus I1 at that side. So I can write this as equation as YA times V1 plus YB times V1 minus YB times V2. And rearranging properly, I can have YA plus YB times V1 minus YB times V2. Now this is equation 1 for me, which is nothing but final equation for I1. Similarly, we can apply KCL at V2 terminal also. So now applying KCL at V2, now I2 is incoming, so minus I2. Rest of the two currents we can take outgoing. Talking about this current, plus it is V2 minus 0 into total admittance in the path, which is YC, plus next this current, which is V2 minus V1 times YB, and this whole equal to 0. I can in fact say I2 equal to, after solving it properly, you will get minus YB times V1 plus YB plus YC times V2. So now this is equation of I2. So again, by comparing with standard equations for Y parameters, you can claim Y11, Y12, Y21, Y22 as I'm showing you. If you refer equation number 1, you can say this is nothing but your Y11. Check it out, this is your Y12. If you notice, this is your Y21 and this is your Y22. So in fact now you can write final Y parameters like this: YA plus YB minus YB minus YB and YB plus YC. So whenever you come across pi network, you don't have to really go for KCL and to follow a lengthy procedure, because in the gate we really have so much time to waste for this. So we basically go for shortcuts. So whenever you have got pi network, you can go for a shortcut. Whenever you have admittances like this, YA, YB and YC in this way, then you can write YA plus YB minus YB minus YB and YB plus YC as direct Y parameters. So this is how we deal with standard networks, whether it is T network or whether it is pi network. For T network, you get directly as Z parameters, and for pi network, you can get directly as Y parameters. The third type that we are going to see is a lattice network. So this is a lattice network. Let's name every impedance connected here. This is considered as standard lattice network, where you can see that this ZA and ZA are equal and this ZB and ZB are equal. In that case, you can write Z parameters directly. So these are the shortcuts to be remembered. Z11 is always equal to Z22 in this case, which is given by ZA plus ZB divided by 2. Whereas if you want to calculate Z12 equal to Z21, they are always equal and given by ZB minus ZA by 2. In fact, we can see a problem based on this, and we will see how to get Z parameters directly for lattice network. So whenever you have lattice network, you can write Z parameters directly like this. So let's see a question. This is 1 ohms. This is 1 ohms. This is 3 ohms provided. Similarly, there is one more impedance like this. Again, this is 3 ohms. And in this, you have to calculate Z parameters directly. So we know the fact that this is matching with our standard lattice network. So I can write Z11 equal to Z22 equal to ZA plus ZB. By comparing with the standard one, you can say that ZA equal to 1 ohms and ZB equal to 3 ohms. So Z11 equal to Z22 equal to 1 plus 3 divided by 2, which becomes 2 ohms, whereas Z12 equal to Z21 equal to Z12 equal to Z21 equal to ZB minus ZA upon 2. So this time it is 3 minus 1 by 2, which is nothing but 1 ohms. So I can write finally Z parameters like this: 2, 1, 1, 2. So these are your Z parameters for standard lattice network. Next question is calculate Z in, where the circuit is given like this. Let's say this is 1 ohms. Let's say this is 3 ohms. Let's say this is 2 ohms. And this is given as 4 ohms. And you have been asked to calculate Z in. As you can see, this lattice network is not going to match with standard lattice network. So how to deal with this? Let's see. Say this is plus minus V1. I'll say I1. And this is plus minus V2. And I'll say I2. But as you can see, since load is not connected here, I can actually say I2 equal to 0. So this I2 value is nothing but 0. So input side, as we can see, V1 and I1. So if I take V1 by I1 ratio, I supposed to get what? I supposed to get Z in. So of course, Z in should be calculated at this end by having a ratio of V1 by I1. Please remember, whenever you actually do these calculations V by I, where V is a source voltage and if I happens to be source current, then it is always giving you Z equivalent between 2 points. So it is going to give you Z equivalent between 2 points. So this is Z equivalent actually. Let's see what we can do with this. Let us assume this point as A. I can say this point as B, this point as C, and this point as D. With respect to A, B, C, D points, we have to calculate Z in between point A and point B. So what I can do is, I can say this is point A and extreme point B. Between A and B, there are 2 extra points. Let's say C and D. Now see, observe this 1 ohms connected between A and C. So between A and C, I'm going to draw 1 ohms resistance. Next, as you can see, 3 ohms resistance connected between B and D. So I can draw 3 ohms resistance between B and D. Next, as you can see, 2 ohms is connected between A and D. 2 ohms is connected between A and D. Let's draw it. And last, as you can see, 4 ohms is connected between B and C. And we have to take the Z in between A and B. So between A and B, if you want to calculate Z in, as you can see, 1 ohms and 4 ohms are connected in series, can be taken as 5 ohms, whereas 2 ohms and 3 ohms are also connected in series, can be again taken as series element, which is 5 ohms. In fact, as you can see, it is 5 ohms parallel with 5 ohms, which is going to give you how much? 2.5 ohms. So I can say ZAB equal to 5 in parallel with 5, which is 2.5 ohms, which is nothing but your Z. So as you have seen, even though we had a lattice network, even though it was not standard, it is easy to solve such problems also. Let's go to the next question now. See, this is called as bridged T network. As you can see, it is actually T network, but along with that, there is extra 3 ohms resistor above the bridge. So it is actually called as, or above the T, and therefore it is called as bridged T network. So we'll see how to deal with this bridged T network. You have been asked to calculate Y parameters. We know the fact that to calculate Y parameter, if we would have been with pi network, then it could have been very easy for us to get Y parameters directly. I'm sure you remember YA, YB, YC. If serially we have as pi network, then I can write Y parameters as YA plus YB minus YB minus YB and YB plus YC. But that's not the situation here. It is not a pi network. It is actually what type of network given? It is bridged network. But ultimately, can we do something to get pi network? Let's see what we can do. If you observe this 2 ohms and 2 ohms are, it is nothing but your star connection. This star connection can be converted into delta connection. So as you can see, this 2 ohms and 2 ohms can be connected into equivalent delta connection. And again, when the values of star are equal, then equivalent delta is nothing but 3 times the Z. Like now you have 2 ohms and 2 ohms as a star connection. In delta, they are going to become 6, 6 and 6. Let's draw equivalent circuit now. It is going to become 6 ohms. This is 6 ohms. This is also 6 ohms. And on top of this, we already had 3 ohms. I'm talking about this 3 ohms, which we already have. And now see, I have completed the circuit like this: V1, I1, yeah, plus minus V2, I2. Now what we can see, these 3 ohms and 6 ohms are connected in parallel. You know the fact that when 3 is parallel with 6, it is nothing but 2 ohms. So I can remodify circuit like this. This has become 2 ohms. This is 6 ohms. And this is 6 ohms. Now see, it has converted into what network? It is nothing but pi network. So now it is very easy for me to deal with such type of circuits. I'm sure you remember when you have YA, YB, YC, it is nothing but YA plus YB minus YB minus YB and YB plus YC. But the problem is, Y has got unit as mho, whereas these units, which is 6 ohms, 2 ohms and 6 ohms, they are in ohms. In terms of impedance it is, right? We have to convert them into admittance level. How do we do that? Just by inversing them. So I can say this 6 can be treated as 1 by 6. This 2 can be treated as 1 by 2. This is 1 by 2, and this 6 can be treated as 1 by 6. Now consider them as YA, YB, YC, or Y1, Y2, Y3. So now I can write Y equivalent directly. You know the fact that you have to go for Y1 plus Y2 first, which is nothing but 1 by 6 plus 1 by 2. So 1 by 6 plus 1 by 2, then minus 1 by 2, minus 1 by 2, and last what you do is YA plus YB, that is YB plus YC, or you can in this case say Y2 plus Y3, which is nothing but 1 by 2 plus 1 by 6. So after solving, what you are supposed to get here? Now this is 6 and this is 2. So you need to multiply numerator and denominator with 3. So it will become 4 by 6, and 4 by 6 can be written as 2 by 3. So this can be written as 2 by 3. minus 1 by 2, minus 1 by 2, and 2 by 3. And of course, every element over here is in terms of mu. See how quickly we can actually solve the problem without actually making it complicated. Students, this is how you should actually deal very smartly with given standard two-port networks. Like it can be T network, it can be pi network, it can be bridge tree network, or it can be something called as lattice network also. I'm sure you have understood all these circuits. Deal with them very smartly the way I have said. Thank you for watching the video.